Welcome, Math 3 students. We're going to be talking about polynomial graphs in this lesson, how to get all the key features of them. I'm going to start the problem with a word problem just to see if we can kind of review some volume. So let's take a look at a box here. We're going to make this box out of good old-fashioned plain 8.5 by 11-inch paper. So what we're going to do is we're going to cut out squares of each corner of the box. We're going to call those squares length x. I went ahead and did that to model this for you. So basically I took each corner and try to get roughly equal size squares. I don't know if you can see it in my video. I'll make it a little bit bigger for you. And in order to make a box out of that, I would simply fold the edges up. And we're going to call this length right here x. Okay, that's going to be the height of your box. So when we're trying to set up a formula, remember that this is going to be three-dimensional. Okay. Now, when we're talking about the height of the box here, we're going to try to make a volume formula out of it. So if you remember the volume formula from just a regular box, it's going to be length times width times height, okay? So our formula, write this down, is going to be 11 minus 2x. It's 11 minus 2x because we're taking two lengths of this x here away from the 11, and we're taking two lengths of this x away from the 8.5. So 11 minus 2x, 8.5 minus 2x, and then x because we got height. X is our height. So we're going to graph this formula in Desmos and find the length of x that produces a maximum volume and figure out that maximum volume. It'll go in here like this, 11 minus 2x in parentheses, 8.5 minus 2x in parentheses and x. And this is going to be a polynomial. It's going to look kind of funky here unless we change the settings here. So I want you to go into the wrench settings right there. And we're going to try to mimic what I have over here. So if you could type this in here with me, you can do the exact same thing I'm doing. So we're going to make the x-axis go from -2 to +8, make it step by 1. And we're going to make the y-axis go from -20 to 80, and we're going to have that go step by 10. And if I did this correctly, I should get a graph that looks kind of like what I got over here. It might not be perfect, but it's a good representation. Now I can see what that value is going to be at that maximum point, and I can see some spots where it hits the x-axis there. You might notice that 4.25 is half the length of 8.5, and 5.5 is half the length of 11. And that's no coincidence. That's by default. Okay, that's by design. So let's go over here and fill in some of these things. So the length of x that produces the maximum volume, well, at that peak there that we got, we had x equals 1.585. So that length of x is going to be 1.585 inches. That volume is the point at that peak. So that volume is going to be that 66.148. And we measure volume in cubic inches. And so that's how you work these problems out. Just the side minus 2x, the side minus 2x times the side, put them in Desmos and get that peak volume right there. All right, now let's talk about key features of the graphs. We're going to write all these down here. I'm going to go back and put these numbers on the graph so we can kind of visualize what's going on here. But first, I want to go back to the graph and hit up a couple other points. So you might notice that it crosses the x-axis at 0, 0, 4.25, and 5.5. And you also notice it goes up and down forever in both directions. So we're going to add those to the graph here. So I'm going to jot these down, 4.25 and 5.5. And that's going to be 5.5. And of course, this is going to be 0. And that 2 is not very pronounced. So I'm going to go ahead and make that 2. Let me erase that real quick and make that 4.25 just a little bit. Okay, I wanted to make those a little more pronounced. I also went ahead and add that coordinate there at that maximum there and put some arrows on the end so you know it's going to go up and down forever. So we want to mark those on your graph on your piece of paper. Now let's go about domain, range, zeros, all that stuff. The domain, well, that's going left and right forever. So the domain is going to be all real numbers. It's going to go from -infinity to infinity. Similarly, the range is going up and down forever. So that's also going to be all real numbers. So we'd write the -infinity to infinity there. Our zeros I already have marked on the graph. I clicked on the x-axis. We're just going to jot them down right here. And so you can write it in the squiggly brackets or just list out x equals 0, x equals 4.25, x equals 5.5. The extrema, those are your absolute mins or absolute max or just relative mins or max. Do we have any relative mins, relative max, absolute mins, absolute max? Well, it turns out that that volume, that 1.585 was a relative maximum. So that coordinate there, 1.585, 66.148 is a relative max. It's not an absolute. This graph doesn't have any absolutes because it goes up and down forever. So no absolutes, just a relative max, but it has a relative min. Can you see where it is? And if you have your graph pulled up, you can click on that bottom point there, and there it is, 4.915, negative 7.648. Now, that doesn't mean anything in this problem, but we're going to write that down for our relative min. I didn't have room to squeeze in the line there, so I just wrote it on the graph here, that relative min 4.915, negative 7.648. Let's review increasing, decreasing, positive, and negative intervals. So increasing interval, well, that's going to be where it's going up as it goes to the right. So if we can identify an increasing interval, let's see if we can figure a couple of those out. And here's one at the very beginning, negative infinity to 1.585 is going up as it goes to the right. Remember, we're only talking about x values. There is another one. Can you find that? And you should notice that the interval is also increasing from the x value of 4.915 forever to the right. So both of those are increasing intervals. Join them together with a little u down there. The decreasing interval is the other one. What's that going to look like? And as you can see here, it's going to be decreasing from 1.585 to 4.915. It's going down as it goes to the right. And so we just kind of write those two numbers in an interval. The positive and negative intervals are cut off by the x-axis. So remember, the x-axis is your cutoff point for those. So you're only going to be focusing on the zeros where it hits the x-axis. Use those to get your intervals. Let's see if we can identify the positive intervals. Anything above the x-axis is a positive interval. There are two distinct ones, 0 to 4.25 and 5.5 to infinity, okay? Your x-axis is your cutoff point, so just pretend we're only worried about those zeros right now. All right, see if you can identify the negative intervals. And here they are. The intervals from negative infinity to 0 and 4.25 to 5.5 are both below the x-axis, so we'd write them just like that. All right, end behavior. End behavior is how the graph acts at the left and right side. So real quick here with this graph, we're talking about on the left side, this graph is going down. So we know that when left represents negative infinity on the x-axis, down represents negative infinity on the y-axis. But then on the right side, this graph, well, on the right side, it's going to infinity, but it's also going up, which is going to represent infinity on the y-axis. So a real quick kind of visual here. Before I get into writing this, I just wanted to provide a visual for y'all. When you're doing end behavior, you look at the left and the right side of the graph. And if the left side is going up, you're going to say as x goes to negative infinity, y goes to infinity. Now, if the left side's going down, you're going to say as x goes to negative infinity, y is going to negative infinity. In other words, x is always going to go to the negative infinity on the left side. On the right side, you're going to say x is going to infinity. And then if it's going up, you say y is going to infinity. If it's going up on the right, y goes to infinity. If it's going down on the right, y goes to negative infinity, but x will always go to positive infinity on the right side of your graph. So when we're making these end behaviors, we're going to write it like that. We're going to write it like this. We say the graph falls on the left, so it's as x goes to negative infinity, y goes to negative infinity. And we say the graph rises on the right, so as x goes to infinity, y goes to infinity. And again, remember this graphic. Take a picture of it, take a screenshot of it. It's going to be super helpful for all your end behaviors. With that in mind, let's go to the next couple examples. Let's go over this example on your own. Well, together, then we'll do the last one where you can try it on your own. Pause video. You first should graph this. So type it in Desmos, pause the video so you can do that, so you can follow along. We're going to get a few key points, and we're going to jot them on our graph. We're going to get all the zeros, negative 1, 0.736. And of course, we're going to jot them on our graph here on your paper. Make sure you list them over here where the zeros are. Next, I'm going to get the extreme points. Looks like I have one max. And we're going to write that on our paper here. There's that point there, 0.351, comma 1.483. That's going to be an absolute maximum because it's the highest value in the graph. Next, I'm going to look at the end behavior. Now, your two gimmies on your end behavior are left and right. X will always go to negative infinity on the left side. X will always go to infinity on the right side. So you're automatically going to write those here. Negative infinity for left and positive infinity for right. Okay, just know that for X, that's what it's going to be. Well, what's it doing on the left side? Well, it's going down. So we say f of x, y, is going to negative infinity. So we write that over here. Remember, f of x can also be y. And there's no problem writing y there if you prefer to do that. How about the right end behavior? Well, this problem is also going down on the right side. So on the right side, it's going down too. Left side, it's going down. We got our end behavior set up. Now let's talk about domain and range for a minute. In polynomials, domain is always going to be all real numbers. It's going left and right forever. So you don't have to even think about that one. All real numbers is negative infinity to infinity. Now the range, that's dependent on your maximums, your minimums. If it goes up and down for it, if its end behavior is going in opposite directions, then the range will be all real numbers. But if you have an absolute maximum or an absolute minimum, then your range is going to limit what values of y can be outputs. So can you think about what your highest y value is in this problem? And it is 1.483. So we're going to have to make our range top out at 1.483. Since it's going down, well, it's going to start from negative infinity until 1.483. How do we write that? Well, we say negative infinity to 1.483, but is it a bracket or parenthesis? Does it include the point? Yes, it does. So we're going to use a bracket. And there's your range. Let's get all the increasing, decreasing, and positive and negative intervals. I'm going to clear some things off so we have a little bit more room to mark. It's increasing at the beginning. So from negative infinity until the x value of 0.351, it's going down to up. So that's going to be an increasing interval. It'll look like that. The other interval is going to be decreasing. It's decreasing from 0.351 to infinity. Remember, infinity on the right side is not down, it's right. So it's got to be infinity over here, never negative infinity. It's got to be negative infinity on this side. So you'll never see this be infinity, and you'll never see this be negative infinity. So those are your decreasing and increasing and decreasing intervals. Now let's identify the positive and negative intervals. First, it's helpful for me to clear off my notations there so we can just focus on the x-axis. There's our dividing line. Looks like we have one interval above it and two below it. There's the one above it. From -1 to 0.736. The two below it are separate, so we'll have to write them separately. See if you can figure out how to write those. Well, did you get the one on the left side right? Negative infinity to -1. That's the one on the left. Now the one on the right, how would we get that? What would that look like? And that's going from 0.736 to infinity. Again, that's a negative interval from x equals 0.736 all the way to the right. Those are below the x-axis for your intervals. Now we got all of our key features for this graph. So you're going to try this one. You're going to pause the video. Graph the function in Desmos exactly as you see it. Pause the video. Try to answer all of these questions, and then you can come back and check with me. But pause it and try it first. I've graphed it. I have the zeros. Extended that just a little bit so you can see the +1. Now I got to mark on the graph, and I'm going to go out of order because since I have the zeros, I can get the increasing, or I can get the positive and negative intervals, but there's just so much going on in this graph, it's hard to mark it all at once. So let's focus on the positive and negative intervals first. Remember, our x-axis is our cutoff point. Where can we find our positive intervals? Well, we got 3 of them. There they are. See if you got them right. All right, let's check the negative intervals. And here are your negative intervals, 0.068 to 1.482 and 2.518 to 3.932. Remember, those are all based on the zeros of the graph. Now, I'm going to get rid of all the stuff on the graph here so we can focus on the other stuff. Let's get our domains, our extreme values. Extreme. There they are. Let's jot them down. Make sure you jot them on your graph. Let's go ahead and glossify them. Now, it turns out those two minimums are both absolute because they are both at -3. And so that's why we call them absolute. They're the very lowest points. So we can get the, basically we can get the range and we can get the intervals that are increasing and decreasing from those values. Let's see if we can get the increasing and decreasing intervals first. I have identified them on the graph. You can see them between 0.586 and 2 x values, and also between 3.414 and positive infinity. It's going to keep going up as it goes to the right forever, so that's why we say infinity. How about the other intervals? Those are decreasing. Well, those are going from negative infinity to 0.586 and 2 to 3.414. So hopefully you're able to see those. Let's get the domain and range. Left and right forever, negative infinity and infinity. Domain's always going to be that. How about the range? Well, the graph has a very minimum point. That point is at -3, and it keeps going up forever. So that range is going to be -3 to infinity because -3 exists on the graph, so we're going to use bracket on that. And the rest, n and left and right, end behavior. Let's see if we can classify those. Well, left is always going to be x is negative infinity, right's always going to be x is infinity. So always have those no matter what the graph looks like. Now, as far as the rest of it goes, well, it's pointing up on both sides. So both the y's are going to go to infinity, so that g of x would just be negative or positive infinity for both. And that is everything. Oh gosh, I hope that was helpful for you. That's all the critical points of any sort of polynomial graph that you'll have to work with. And go ahead and try the practice assignment, the 3.6 practice assignment on your own. Thanks for watching.